Welcome to our program on grounding and shielding of electronic systems. This program consists of 15 sessions. The first session, which will begin in just a moment, is concerning the path of least impedance. The second session will be on electrical noise coupling mechanisms. Then we'll discuss the equivalent circuits for noise problems, how and why to ground electrical systems, and we'll look at several signal grounding examples. We'll have a review a bit later on, summarizing the first 5 sessions. Then we'll get into how to diagnose noise problems. Diagnosing a noise problem, very important topic, probably the central theme of our whole program. We'll talk about impedance balancing and common mode rejection, filtering of conducted noise, self-shielding. Self-shielding is one of my favorite topics. It's a little different than the normal shielding techniques most people are aware of. So we'll spend some time on that in a later session. Electric field shielding. Where to connect the shield on a twisted pair cable. That's a very critical, very often confused issue. Do you ground the shield on the source end or the receiving end or both ends? We'll spend some time showing you the reasons behind and how to connect the shield on a twisted pair cable. We'll talk about magnetic field shielding. This we'll find is an expensive, difficult thing to do, especially at low frequencies in the kilohertz range. Now in the megahertz range, magnetic field shielding is not so difficult. Electromagnetic wave shielding, keeping those 200, 500 megahertz frequencies under control. We'll take a look at that. Shielding, or selecting rather, the right type of cable for the particular application. Should we be using twisted pair, coax, ribbon cable? Which would be the best for the application? And then we'll conclude with a couple of sessions on circuit board layout. For now, let's begin discussing the path of least impedance. This is sometimes a simple concept, at least thought to be simple, but it's much more complicated maybe than we realize. This whole program is based on about a dozen key simple principles. One of them is, where do currents go? We like to say often that currents go to ground. That's not a very good idea because that's not what happens most of the time. Currents actually return back to their source. So we want to keep that idea in mind. Every current returns to its source. Sometimes we say, well, what about antenna currents? What about the case of a dipole antenna? Do those currents really return back to the source? I think they do, as illustrated in this example here. We have a source driving a dipole antenna. We have conduction current on the wires, and that's the current we normally concentrate on. But in the air, between the wires, there's a capacitance, and there results in displacement current back to the source through that capacitance. So if we look at the combination of conduction current on the wires, displacement current through the air, I believe again we'll conclude that even for antennas, the current does return back to its source. In a moment we're going to do a demonstration using this coaxial cable, but for right now we'll just talk about the situation and what we think is going to happen when we do that demonstration. Imagine a piece of coaxial cable about 3 feet long. The dotted line represents the center conductor inside the coax. The solid lines are the outer conductor. We have a load resistor on one end. That resistor, along with the source, determines the amount of current that will flow on this cable. Now, the amount of current on the cable is a functional issue. If we don't have the right signal level, then there's a problem there. But from an electromagnetic compatibility, or EMI point of view, we're often concerned not just about the amount of current, but the precise path of the current. The path is extremely critical to us. We may have everything functioning properly, but if a small amount of this current goes in the wrong place, then this current is likely going to cause us an EMI problem. So in this case, we're trying to figure out what is the actual path of the current. We're assuming a relatively high frequency, several megahertz, 10 megahertz in this situation. And if it's a clock signal, well, of course, it's got harmonics at 30, 50, 70, 90 megahertz and so on. So a moderately high frequency current. What path is this current going to take? The current is going to go down the center conductor of the coax cable. it's going to have some capacitive coupling to the outside conductor. But we're going to neglect that. We're going to assume that the bulk of the current makes it all the way over to the end of the cable. Now the question is, when the current gets to this node here, how does it return back? It's got two paths. We have a short wire, about 2 inches long, connected between the two coaxial connectors. The current can take the short path, or it can return on the outer conductor of the coaxial cable. Well, we normally say current takes the path of least resistance, and that would seem to indicate maybe the shorter of the two paths. But that turns out not to be the best way to think about the problem. Let's take a bit of a look at what path current takes, and then we'll come back to our example with the coaxial cable in just a moment. Current actually takes the path of least impedance, not least resistance. Least resistance is a special case. We'll see in a moment that this is true primarily for low frequency, a few kilohertz or less. But for several kilohertz and more, higher frequencies, least resistance is not the correct idea. For wiring, which is mostly what we're going to be talking about, and this wiring, it doesn't matter much what it is. The wiring we're discussing could be the twisted pair, it could be a coaxial cable, it could be a ribbon cable, any kind of wiring. It really doesn't matter. The imaginary part is the reactance, and the real part is the resistance. And we're interested in which of these two parts dominates, the resistance or the reactance. So we'll be concentrating on which of those two parts determines primarily the impedance of the path. This figure right here, this equivalent circuit for our two-conductor wiring, might actually be the most important figure in this whole first session. We're going to spend several minutes now explaining where this came from and what it all means. In fact, I think what I'll do is I'll just redraw this for you, starting from scratch using a blank sheet of paper here. Let's assume we have two conductors. Each one of those conductors has resistance. And I think we would all agree with that. That's a measurable parameter. Those resistances are individually, independently measurable. Now, in the equivalent circuit I just showed a moment ago, those two resistors have been put together in series to represent one equivalent resistance. I don't believe we have any problem with that. Now, between the two conductors, there's one capacitance. Now, we're assuming that either the wires are electrically short, or if they're electrically long, then this is the capacitance per unit length for a short section of wiring. So far we have two resistors, one for each wire, and a capacitance between them. That's the easy part. The hard part is the inductance. How do we think about that? Well, I think most people think about it incorrectly. They say the top wire has self-inductance L1. The bottom wire, they say, has self-inductance L2. And between the two wires, they would say there's mutual inductance M. I don't believe that's the case. Self-inductance is a property of a closed path. And in this situation here, if we were to short these two wires together, we would have one loop. One loop, one closed path, we would have one self-inductance, not really two self-inductances with a mutual inductance between them. So the way I want to show this, my equivalent circuit, I want to show the two resistors combined together into one. I want to show the self-inductance of the one loop that we're discussing, and then I want to show the capacitance between the two wires. There really is only one self-inductance. Now, if you look at the R and L in the shaded box, think of that element, those two elements making up an impedance on their own, you'll find out that the reactance, 2 pi FL, will exceed the resistance when the frequency gets above a few kilohertz. Usually it's around 3 or 4 kilohertz. We'll see that in our demonstration in a moment. So in many wiring situations, once you get above a few kilohertz, the inductance seems to be the dominating factor. I have a few formulas for you just to show you what inductance really depends upon. If you have two parallel wires, if they were shorted together, and if the wire length was large relative to the spacing, and the spacing between the wires was large relative to the radius, then the formula would be simply the inductance would be proportional to the length of the wire and logarithmically proportional to the separation divided by the radius. So you increase the lengths of the wires, the inductance increases. You increase the separation, the inductance increases. You increase the wire size, the inductance decreases. Now, I know many of you don't have a need to calculate in detail the inductance, but once in a while some of us do, so I've thrown out a few more formulas here to show you different inductor values. These formulas now are the inductance per unit length. You have two parallel wires. That's the situation we were just talking about. This is the representation for the inductance. You have a wire above a plane. Again, if the plane is fairly wide compared to the separation between the wire and the plane, you can use this approximate formula. Two parallel plates, wide relative to their separation. Very simple formula for the inductance per unit length of two parallel plates. And here the inductance for the coaxial cable. With these few examples right here, you can approximate many of the situations for which you might be interested in calculating the self-inductance. All right, let's go back to our example again of the coaxial cable. What path is the current going to take on the coaxial cable? Well, it depends on the frequency. And if we're talking about, in this case, megahertz frequencies, then we expect the current to take the path of least impedance, which will be least inductance, which actually amounts to the smallest loop area. So we're looking for the smallest loop area. The current goes down the center conductor, through the load resistor. It could return across the short wire, but if it did, all of this area here would be the area involved in the current path. And that's a relatively large area compared to what is available. Instead, if the current returns back on the outer conductor, like here, then the loop that's involved will be on the inside of the cable. It's a little hard maybe to imagine these two different loops. Maybe when I show you the cable in a moment you'll be able to see it a little better. But there are two possible paths. One, the current goes down the center conductor through the load resistor, crosses back here. This entire loop is part of that path. A large loop area means high inductance. The other path is the current goes down the center conductor, returns on the outer conductor of the coaxial cable. In that case, the loop is the radius of the cable multiplied by the length of the cable. A much smaller loop area, meaning much smaller inductance, and that's going to be the preferred path for the current. Let's check this out with a demonstration now. We're going to use the same figure, and I'll show you now the coaxial cable here. We've got high frequency signal coming in on this connector, and I have a cable 3 feet long coiled up here. The coiling of this cable does slightly increase the inductance of the larger loop, not the internal loop, but the larger loop. So right now we're sending a signal. It's a 1 kilohertz frequency that we're sending in here, and we're trying to figure out what path this current's going to take. The current's going to go down the center conductor of the coax, around the cable, back through the load resistor. And at low frequency, we expect to find most of the current taking the short path back to the source. We use a clamp-on current probe to see what's going to happen here. So we'll take a look at the current through the resistor. This clamp-on probe is giving an output you can see on the upper corner of the screen. That's actually a voltage, but that voltage is related to the current through the wire that the clamp-on probe is around. That's the total current to the load at 1 kilohertz. Let me now move the probe over to this conductor here. Get it to make contact there. There we go. We don't have 100% of the current here. We have about 60 or 70% of the current. The majority of the current is taking the short path, but some of the current is returning on the outer conductor of the coaxial cable. But this is at 1 kilohertz. At 1 kilohertz, we expect the resistance to dominate the path. Let me increase the frequency. I'll go up to 10 kilohertz. Let's again check how much current is there through the resistor. We just pay attention to the peak-to-peak value. That's all we need to concentrate on. That peak-to-peak value represents the total current through that resistor. All right, let's now compare how much of this current is on the short path. Now maybe 20% of the current is on the short path. 80% of the current is coming back on the outer conductor of the coaxial cable. And this is 10 kilohertz. So somewhere between 1 and 10 kilohertz, the inductance started to dominate, and the current started to determine its path based on which has the least inductance. Let me just go to one more higher frequency. Go up to 100 kilohertz. Let's see how much current we have through the resistor. It's basically the same amount of current we've had in the previous situations. We have the same source voltage, we have the same resistor value, roughly the same amount of current. So how much of that current is coming back on the short conductor? Well, almost none. Actually, there's a very small amount of current. If we increase the sensitivity of the scope, we can see a little something there. But now, we'll say 95% of the current is coming back on the outer conductor of the coaxial cable. That represents, again, the smallest loop area, the smallest inductance, and that's the smallest impedance. Okay, we've tried this with a coaxial cable. Let's go over to a little different situation. Let's try a twisted pair cable. It should be a very similar result if what I've been saying is true, if what I've been saying holds up. So we'll switch over to the twisted pair. All right, we have a similar situation. We have a connector coming in here where the signal comes in, and I'll set the frequency back to 1 kilohertz. And the signal goes out along this twisted pair cable, and it happens to be looped again, and comes back to a load resistor mounted right in here. The diagram underneath shows roughly what we're looking at. This will give you an idea of the overall picture if I don't block it from your view, but you have it in your notes anyway. We're sending a signal in. We're going to start out at 1 kilohertz, and it's going down this 5 or 6 foot long piece of twisted pair. The amount of current is dictated by the load resistor. The cabling is not determining the amount of current. It's determining the path of the current. And I have a little chart here that I've already filled out, but we'll just redo part of it anyway. We're going to measure this time the current at 3 different locations: the current through the resistor, the current on the short path back, and the current returning on the second conductor in the twisted pair. We'll start out, as we said, at 1 kilohertz. Let's look at the current to the resistor. That's the amount of current to the resistor. We'll say, when I read this previously, that was 158 millivolts. I won't check it this time. We'll assume it's about the same this time. That's the total current. That represents the total current. How much of the total current is on the short path? Well, again, not all of it, but the majority of it. Say 120 volts, 120 millivolts worth of the total current. How much does that leave for the other path in the twisted pair? Well, probably the difference between the two, which in this case is about 22 millivolts. These do not add up exactly to be the total of 158, but they're fairly close. At the higher frequencies, it works a little better, I believe. Anyway, at 1 kilohertz, even for this twisted pair, the current, again, is almost always going to take the path of least impedance, but at 1 kilohertz, for the twisted pair, it's the path of least resistance. It's the short conductor right across here. Let's try 10 kilohertz. 10 kilohertz, how much current do we have to the resistor? That amount of current, which we'll say again is about 150 millivolts on the scope. How much current goes on the short path? Now it's quite a bit less. Now it's down to maybe 60-some millivolts. But how much current's on the return or the second conductor of the twisted pair? Majority of current there. In fact, maybe it's even a little larger than what I'm writing down in this case here. But now we're at 10 kilohertz, and again at this frequency, the path that dominates is the one with least inductance. It's not the short path. And we could try one more time at higher frequency. I will just try 100 kilohertz. I've also got the results for 1,000 kilohertz or 1 megahertz. But let's try 100 kilohertz. There's the current. It's, again, roughly the same current at all frequencies, roughly the same value. How much of this current now is on the short path? Maybe 50 millivolts worth. How much of it's on the other conductor of the twisted pair? Yes, the majority of it returns on the low inductance path in the twisted pair. What we're finding here is something that's very simple. Current takes the path of least impedance, not least resistance, at least not normally. Now, what determines the path of least impedance? That depends on the frequency. If the frequency is below 1 kilohertz, it's pretty sure current's going to take the path of least resistance. If the frequency is above 10 kilohertz, again, we can be pretty sure current's going to take the path of least inductance. Now, between 1 and 10 kilohertz, it's a little hard to decide exactly which one dominates. Usually around 3 or 4 kilohertz, one is about as effective or has as much contribution as the other. Okay, let's try this on an example. Let's take a look at this 2-layer circuit board. And it could be a 12-layer circuit board. It doesn't matter. The particular current that we're looking at here happens to be some kind of a clock-type signal, we'll say. And this clock signal, if this were a 12-layer board, hopefully would not use all 12 layers. Hopefully it wouldn't even use 4 or 5 layers. That clock signal would use 2 or maybe 3 layers of the board. So this could represent a simple 2-layer board, or it could represent a signal on a multi-layer board that happens to just use 2 layers. The question again is, what path is this current going to take? Well, we have a trace coming from the clock oscillator or micro or whatever device provides this clock signal. There's a trace out over to this IC. We're pretty sure the current's going to take that path. At least if it doesn't take that path, then we got a functional problem on our hands, maybe as well as an EMI problem. But from this point of view, from our point of view here, we're trying to determine where the current goes and does it go where we want it to go, and do we know where it goes, and are we able to then control our EMI problems. The current goes into this integrated circuit chip. Now, it has to come out somewhere. Electrons just don't get stored up indefinitely. They've got to come out. The trouble sometimes now with our larger packages that have multiple, well, we call them ground pins. Later I'm going to tell you I don't think that's the right way to think of it. I think of them as return pins. But with multiple ground pins, we're not always sure exactly which pin the current comes out on. In fact, it may come out on several of the pins. And in fact, high-frequency clock currents may come out on other signal pins as well as the ground pin. So we're going to assume here that we know that this current comes out this particular ground pin and goes to this via. The via just being a plated through hole to the back side of the board. The back side of the board is a solid metal sheet. The question now is, the current's gotten to this point in the metal sheet. How does the current get to this point, the via that returns the current back to its source? Remember, we said all currents eventually go back to where they came from. Well, in the case of a clock signal where we'll say it's in the megahertz range or higher frequency, we know then to be looking for the path of least inductance, not least resistance. Least inductance is the smallest loop area. So that means the majority of this current follows this trace directly back underneath the trace and comes to the via at that location. By coming back underneath the trace, that's the path of least inductance, the path then of least impedance. What if this clock signal had been, say, a 1 kilohertz clock, which is not so used normally these days, but what if it had been a very low frequency signal? Then the current would take all paths back. Some of the current would come here, some would come there, and some would come there, and some would come there. The path of least resistance sometimes can be a problem for us because that may mean that the current takes all paths available. Okay, let's do a little more discussion of these two conductors. This modeling of two conductors is very important to us to understand where currents are going to go and will they be in the right location. These two conductors carry one current, not two currents. They carry one current out, one current back. We usually call that a differential mode current. We'll talk about differential mode and common mode in some detail later. We said the model for these two conductors is in this case, distributed series inductance and a distributed shunt capacitance. There's resistance here also, but I'm assuming compared to the other elements that this is negligible or not that important to us. So the question is, how do we think about these inductors and capacitors we've shown here? And do they have any relationship to one another? Turns out they do. If you change the spacing between the wires, the inductance is going to change. For example, let's use my arms here. if my two arms represent two conductors, if I pull these conductors farther apart, we know the shunt capacitance between them is going to decrease. But we also know, I think, if we pull the conductors apart, the loop area gets larger, the inductance increases. So we can use the loop area idea we've already developed to help us figure out, what's happening to the wiring inductance. But there's another way to figure this out. We can relate it to the wiring capacitance. So let's take a look at the next figure and see how this inductance is related to the wiring capacitance. The phase velocity, which is just the velocity of a single frequency sine wave that you would put down that cable, the phase velocity can be shown from simple transmission line ideas to be related to 1 over the square root of LC. Now, we're obviously not proving that. We're assuming that you can check that out if you were interested by looking at some basic transmission line ideas. This assumes pretty much a lossless line, which most transmission lines are pretty close to lossless. So this is an idea we're going to assume we know. Now, if you look at it another way, the energy on that's being carried by these two wires, we don't think of the energy as in the wiring. We think of the energy as in the magnetic field around the wires or the electric field between the wires. So if you look at it from a field's point of view, and you say, well, what determines how fast the energy is going to move, the velocity of this energy? Of course, maybe I should point out here, energy velocity and phase velocity sometimes are not the same, but we'll assume for the moment that they are here. It's the material properties. The material properties around the wiring determine the essentially speed of light of electromagnetic waves in that material. So we take a look here, we'll find that the velocity can also be written as 1 divided by the square root of mu epsilon, where mu is the magnetic permeability and epsilon is the dielectric constant, or sometimes called permittivity, of the medium. So what this tells us is these two expressions are equal, therefore the LC product, the product of the distributed inductance times the distributed capacitance, that product has to equal the product of the wiring parameters, and this is really the insulation of the wires and maybe the air around the wires. It's not the wire itself, but it's the parameters of the insulation and dielectric materials around the wiring, and that product in most instances is constant. Not in every case, but in most cases. So for wiring, the LC product is constant, approximately constant. And that's a very good, very useful idea. We're going to be able to make a great deal of use out of that in other applications. Now back again to this idea, what path does current take? I know I keep stressing this, but this is crucial. Most of our EMI problems, electromagnetic interference problems, are caused by either signal or power currents not going where they're supposed to go. Or maybe somebody else's signal currents don't go where they're supposed to go, and they wind up in the midst of our cabling system where they don't belong. So this idea of needing to keep a close track, a very close track, on exactly where the currents are located is critical. If you're working in a wiring harness, with a wiring harness, it's the same as whether you're working on a circuit board. We have to know exactly which wires are going to carry the signal currents and the power currents, and on the circuit board we have to know exactly where those currents are located. Now, we've already said if the frequency is below a few kilohertz, the current's going to be dominated by the resistance of the various paths available. If the frequency is above a few kilohertz, the current path is going to be dictated by or dominated by or controlled by the various inductances of the paths that are available. So we know now how to think about this and how to look at this. Well, the problem here is with low frequency currents, DC to a kilohertz or so. What path do those currents take? Well, I want to say path of least resistance, but actually the way I ought to think about this is low frequency currents take all possible paths available. That can be a real serious, troublesome problem. If we're not aware of that, we're going to realize maybe that the signals are, maybe 98% of the signal current is going where we wanted it to go, but a few percent is going off in some other path because there happens to be a shunt parallel path to the one we had intended, and that little bit of current going elsewhere could be a problem. So low frequency currents, Think about them as trying to take every path available. That can get us into a great deal of trouble when currents do that. At higher frequencies, 10 kilohertz and higher, actually in many cases the situation is simpler. Then currents take the path of least inductance, which means the smallest loop area. Now, of course, if there are multiple parallel loop areas, meaning that there are parallel inductive paths, then the current will divide inversely proportional to the inductances of the paths. At least in the first simple approximation, they will do it this way. And that can lead to a little bit of trouble. If we have a low inductance path where we want the majority of the current to go, but a parallel higher inductance path, some of the current will take that other parallel path. And that's what's usually going to lead into the electromagnetic interference problem. That little bit of current taking the unintentional inductive path. Let's try this example. We have a flat ribbon cable, say. And we've got multiple signals on this ribbon cable, but we're just primarily interested in one of them at this time, called signal number 1. The other dashed lines represent other possible signals that, again, we're not currently interested in. Let's say that signal 1 has a frequency of 1 kilohertz, a low frequency. What's going to be the return path for this signal? Well, we have 3 equal resistance return paths, and therefore the current's just going to divide equally between those 3 paths. Just a simple division based on the relative resistances of the paths. But now what that means again is the current spreads out across this ribbon cable. If there were several more return wires in the cable, then the current, the low frequency current, would use those as well. But now let's see what it does at higher frequency. Say this was a 1 megahertz signal going down line 1. Well, then we'd have to look at the relative inductances of the paths. We have one loop here, which I've designated as having self-inductance L1. We have another loop, which I've designated as having self-inductance L2, and we have a third loop. And then I used one of the previous formulas we've talked about to calculate the self-inductance of these 3 different loops. And that's written in the notes that you can see that. Using those inductance values, I've determined that about 56% of the current will take this path, and about 25% of the current this path, and about 19% of the current this path. Now these are just approximate values. I did neglect the mutual inductances between these loops, and at the higher frequencies maybe that could be pretty important. And actually I said this signal might be 1 megahertz. Those mutual inductances could have quite a bit of an effect. I think what you'll find is that the 56% estimate will be low then. There will be even more current using this lower inductance path if we included mutual inductance effects. But anyway, the idea is that at higher frequencies, the inductance, first of all, dominates. And you tend, of course, to have more of the current coming back on the low inductance path. But, unfortunately, there is some of this current taking these other paths. And we may have to worry about that. That can result in additional crosstalk between signals 1 and other signals in the cable. Also, this little bit larger loop area than we might have been anticipating is going to result in a little bit more magnetic emission than we would have liked. All right, well, we'll switch over to another topic for a few moments. We'll talk a little bit about decibels. This is a confusing idea for some people, and we'll see if we can straighten it out a little bit here. The decibel started out as the ratio of 2 power levels, and it had a lot to do with how the ear hears sound. But anyway, it starts out as the 10 log of the ratio of 2 powers. You hear people talk about dB milliwatt, or dBm. dB milliwatt would be a power level measured relative to a reference of 1 milliwatt. 10 log of a power relative to a milliwatt. Now, voltage is usually related to power squared, but it's or voltage squared is related to power, V squared over, say, an R. If you got V2 squared over R and V1 squared over R, if the 2 resistances are the same, then they can be canceled out, and the squares can be brought out in front and get 20 log of the voltage ratio. Now, a lot of times, the resistances across which we're measuring these 2 voltages, the resistances may not necessarily be the same. We often ignore that fact and go ahead and use 20 log of the voltage ratio anyway. If we want to use a reference level for our voltage measurement, let's say in this case a reference of 1 microvolt, then we would say we would be calculating a dB microvolts. This just indicates the reference level for the voltage calculation. And also, we could calculate the decibel levels for electric fields, for currents, for magnetic fields, and we do it in a similar manner. Any quantity that's related to power squared, the quantity squared is related to power, we use 20 log of that ratio. So we could talk about electric fields in dB microvolts per meter. That's relative to a microvolt per meter. Well, since EMC type people, electromagnetic compatibility people, often speak in terms of decibels, we need to be able to talk in that language a little bit as well. Now we're going to be interested in this program in reducing noise problems, decreasing noise levels. How much noise reduction do we think is a significant amount? Is 2 dB noise reduction significant? Well, if it's the last 2 dB you need to pass the spec, we're going to say it's quite a bit. It's just what we want. But in most situations, 2 dB is a relatively small change in noise level. We're going to be needing usually a lot more than that. So I'm going to be assuming that we're going to be shooting for more like 10 or 20 dB. Now again, we may not ever achieve those numbers, but that would be more thought of as a significant reduction in noise level. So how do we get 20 dB reduction in noise level? Well, we go back to our expression for dB voltage, especially this one. If we reduce the noise voltage by a factor of 10, then 20 log of 10 is 20 dB. So 20 dB, when you're talking about a parameter that's related to power through a square function, to get 20 dB, you have to change that parameter by a factor of 10. Now we're going to want to know what parameters to change. What do we have to do to fix the problem? Well, in a later session, we're going to show you the various noise coupling mechanisms that can occur and the equivalent circuits that describe those problems. And once we know the equivalent circuit, we will then know which circuit parameters influence the problem. For example, we will see later that with electric field coupling problems, the voltage of the noise source is important to us. The mutual capacitance between the noise source and the susceptible circuit is important. The frequency is a factor, and the impedance of the susceptible circuit. Those will be parameters that will show up in our equivalent circuit, and therefore they will tell us that those are the parameters we need to try to adjust, one of them at least, by a factor of 10 to try to get 20 dB. In an electric field coupling problem, we don't want to be adjusting necessarily the current. It's not directly related to that problem. Nor would we want to be worrying about the mutual inductance when we have a capacitive coupling problem. So once we know the equivalent circuit, then we'll know what problem we're dealing with, and that equivalent circuit will show us which parameters we need to adjust in order to try to get our 20 dB of reduction. Of course, if you can't change something by a factor of 10, then you try a factor of 6 or a factor of 2. 20 log of 2 would be 6 dB. You can back down from this a bit to do whatever you can manage to do, but I would say you don't want to approach a significant noise problem by trying to change something by 5%. That kind of a change is not going to result in enough dB reduction to make it a significant improvement. Just a couple of quick practice examples here. We said 20 log of 10 is 20 dB, 20 log of 3 is approximately 10 dB, 20 log of 2 is approximately 6 dB. You could use, with these three values, you can just about estimate the value of any ratio. For example, say you want to know the ratio 60. What is that in logarithmic terms? 20 log of 60. Well, you could write 60 as 2 times 3 times 10. And of course, when you have the logarithm of a product, that's the sum of the logarithm values. So you take 20 log of 2 is 6, and 20 log of 3 is 10, and 20 log of 10 is 20. We get 36 dB as approximately the value for 20 log of 60. With these three values, if you know those three, you can rough out approximately the values for any others that you might need to work with. Again, another practice example. Supposing we had 1 volt and we wanted to write that in terms of so many dB microvolts. Well, we take 20 log of 1 volt relative to a microvolt, 20 log of 10 to the 6th, 120 dB. 120 dB microvolts, yes. Now, if someone just said, I have a voltage level of 120 dB, they said that was the voltage level, 120 dB. Well, that doesn't tell us what the value is. We don't know necessarily the reference level they were using. Maybe they intended it to be dB microvolts, but maybe it's dB volts. Of course, that could be a big difference. We need to know that, wouldn't we? So if there's no unit associated with the decibel, then either there is no reference particularly, or we don't know what the reference is. Now, actually, if you look at this unit, this quantity over here, you'll find out that theoretically, officially, this is a dimensionless quantity. This does not have units. But the way we usually say it is we say dB with some unit given to show us what the reference value is. How is 1 watt related to so many dB milliwatts? Well, take 10 log this time because we're working with power. 10 log of 1 watt over a milliwatt, and it's plus 30 dBm. Okay, now back to the original question we started this session 1 with. What path does current take? This is all there is, really, I think, to controlling noise problems, is concentrating carefully and completely on the path of the current. We have a signal path to an amplifier. We have a return path. Maybe it's a twisted pair. Maybe it's just a wire and a ribbon cable. But anyway, we have 2 paths that we're hoping the current's probably going to use. But unfortunately, the receiver is grounded, and the sensor, or driver, is grounded. And that means that between those two, there is a connection of some sort. Maybe it's a fairly lengthy and distant connection, but there is a path. So what does the current do if the frequency is 1 kilohertz? Well, then the current divides depending upon the resistance of the 2 paths. And maybe we'll have, I was going to say 60% of the current here and 40% of the current over here in what might represent a ground path. But if this is a grounding structure, likely these wires out here could be much larger sized, much lower resistance than the signal wire. Let's say this right here turns out to be a number 22 gauge wire. Let's say this is the 4-aught conductor here. Well, then what are we going to have? We're going to have then we're going to have 90% or more of the current there, and only 10% of the current coming back there. It's just a matter of resistance. And in this case, the grounding path could have much lower resistance than the intended signal path, and now we're in a lot of trouble. See, now the majority of our current takes this large loop, a loop that we don't even know what it is, a loop that's probably big enough to park an 18-wheeler inside of. And when loops are that big, they're just flat out too big. That loop is going to emit magnetic fields, and it's going to be able to receive magnetic fields, a major problem. So the low-frequency current in this case is going to be a troublesome one. What do we do for low-frequency currents? We don't give them alternative paths. Low-frequency currents, the best way to think about them is they will take every path available. Not exactly to the same degree, but they will take every path available. So make sure that if you want a low-frequency current, that's anything below a few kilohertz, you want that current to take a specific path, the best idea is to only give it that path. No other path possible. High-frequency currents, you see, are a little better behaved. And high frequency, say we go up to 10 megahertz, my drawing's getting a little cluttered here, but if we had this same situation with 10 megahertz, then we're going to have 90-some%. Maybe it'll be the other way around. Now we're going to have 90% of the current here, maybe 10% of the current over there. Of course, that could be a problem too. Much less current taking the large path, but much higher frequency. So we still got to worry about this a little bit. But actually, my estimate of 90% of the current on the desired return path, maybe that's a little bit low. It could be that it might be 98%. But still, there's going to be, at 10 megahertz, there's going to be a little bit of current wanting to use this other path. And we want to do whatever we can to make that path less desirable. We want to add some impedance possibly in this path. We would probably call this a common mode current, and we would add some common mode inductance if possible to this path. Of course, the best way to get rid of these alternative paths would be to unground, say, the receiver. But we got to make sure we don't create a safety hazard when we get into doing that. In fact, the next session we'll talk about some of the safety issues. Again, where do currents go? Here we have a simple situation where we have a signal intended to go to this load with an intentional return path. But for some reason, there's a little bit of metal hanging off on this side and a bit of metal hanging off on that side. Let's say this is a 100 megahertz frequency, a very high frequency here. Well, then what will happen is this current Of course, now some of it capacitively couples over like that, but the current, part of it will go through this resistance, but a little bit of it will go through this capacitance between the two pieces of metal hanging out there. We call current through a capacitor displacement current. So our intended conduction current, what it does is it splits up into a partially conductive path through the resistor and, unfortunately, a much unintended displacement current path through the capacitor. This displacement current is what is likely to lead to electromagnetic wave radiation. Sure, 98% of the current may go exactly where we intend, but if 2% goes out in this area here, that is likely going to be the entire EMI problem, that 2% getting out of control. If we understand that, maybe we can realize that these pieces of metal hanging out here, maybe if they were something that didn't need to be there, we could reduce that metal surface area, reduce this unintentional capacitance, and partially control our radiation problem. Let me do a few ideas that are not in your notes, but you're probably aware of anyway, but I just go over these quickly to let you remind you of a few things. When you see this color paper, you'll know that this is a sign that the figures are kind of extra examples and that are not in the notes. Let's try to get an idea of the bandwidth of a typical pulse wave shape. Now this actually probably isn't typical. I've got this represented as a trapezoidal type wave, a nice clean straight edge here with no ringing and so forth. So we don't see signals that look quite like that, but as an approximation we can start with this. So we've got a rise time and a fall time, and I just mentioned the rise time, but what we would do is we'd pick whichever edge is shorter, whichever edge is fastest. That would be the controlling factor. We want to know the frequency content produced by this time domain waveform. What does it look like in the frequency domain? Well, if you're familiar with Fourier series for periodic signals, then we can use that information to figure out what's going to happen here. Here we're plotting amplitude, logarithmic amplitude versus log frequency. There'll be a fundamental second, third, fourth, fifth harmonics coming across here. And what I've done is I've connected the peak values of the harmonics. I've connected the peak values together to get an envelope shape. This first breakpoint is determined by the pulse duration. Beyond that frequency, the amplitudes fall off at 20 dB per decade. The next breakpoint is determined by the pulse rise time or fall time, whichever is fastest. Again, we pick the sharpest edge, that's the critical edge. Beyond this frequency, the roll-off is 40 dB per decade. Now what we often will say is the roll-off of 40 dB per decade means that beyond this corner frequency, we don't have to worry much about those components. Well, if you had two equal level digital signals, and you were worried about one cross-coupling over to the other. Say they're both 3.3 volt digital signals. By the time you get above that second corner frequency I've identified there, you will not have enough energy from any one of those frequencies that if it couples over to the other signal, it'll be enough to shift the logic level. So for equal amplitude type signals, that second corner frequency pretty much indicates the limit of the upper frequencies we've got to worry about. But you see, most EMI problems are not like that. Some of the worst EMI troubles are where you've got, in the case of a cell phone, you've got a digital circuit trying to couple into a very low-level analog RF circuit. So the signals that are competing with one another are not at all near the same level. In a situation like that, or you've got a case where you're trying to pass a very tight emission spec, if the energy beyond this second corner frequency, if that energy gets turned loose, it's going to likely cause us to fail the emission spec. So what we would say is, these frequencies up here, do we have to worry about them or not? It depends on the situation. I think you will know whether you need to be concerned about them. Many people, many of us, do need to be concerned about these frequencies that are beyond this limit. But at least that limit, this frequency right here, gives us an idea of roughly where we are in the spectrum. As an example, we're using this upper frequency we were talking about that's determined by 1 divided by pi times the rise time, again, or fall time. If we had a 1 nanosecond rise time, this frequency would be roughly 300 megahertz. I guess officially it'd be 318 megahertz, but we are rounding things off here because we don't have situations that are that precise, that are that well known that we can calculate them out to 2 and 3 decimal places. So roughly 300 megahertz. That's most of the energies below that frequency. But what if we're trying to pass an emission spec? We probably then have to worry about frequencies that go, I would say, up about 10 times this. That's the rule of thumb that I use. I would go up to about 3,000 megahertz with my concern about possible emissions. So this calculation right here, it's approximate, but it does give us a rough idea of what frequency range we're dealing with. Most energy is below that, but there is energy that goes about 10 times above this frequency that you may have to be concerned about in some situations. Another idea you're probably aware of is the wavelength. We can calculate wavelength if we know the frequency of the signal and we know the velocity, the phase velocity, in the medium in which the signal is propagated. So as is shown in this figure here, we know the frequency and the phase velocity, we can calculate the wavelength. The reason we'll be interested in the wavelength is we often need to know how big things are. And big is a relative term. Relative to what? Well, probably electrically it means somehow relative to a wavelength or a fraction of a wavelength, something like that. Well, at 100 megahertz, we take the wavelength. To get the wavelength, we take the speed of light, in this case we'll assume air, divide by 100 megahertz, gives us a frequency of 3 meters. So in air, 100 megahertz has a wavelength. Did I say frequency? Has a wavelength of 3 meters. All right, wavelength of 3 meters. Now, is 3 meters then electrically large? Well, let's see. If we have a dipole antenna, and this L is the length of the dipole, if that length is a half wavelength, we know that that antenna will transmit and receive very well. We know it's a very good antenna, transmitting and receiving. So a half wavelength, I would say, is electrically large. We also know that monopole antennas, the length in that case for a monopole is a quarter wavelength. Of course, it uses the ground plane as a mirror reflecting surface. It's actually trying to act like a half wavelength dipole. But anyway, a monopole, quarter wavelength long, that's electrically large. The rule of thumb I like to use is I take a half wavelength, divide by 10 to get a wavelength over 20. And I say that when the length of a cable, the length of a trace, the length of a component, when it's less than a wavelength over 20, then I think we can say it's electrically small. Now this is approximate again. There will be situations maybe where this is not quite small enough to completely ignore the radiation that might be coming off of this structure. But in most cases, I think we'll find that this is a very practical, useful idea. Wavelength over 20. For those of you who are the theorists or the purists among us, you may want to go look up your antenna theory, look at the radiation resistance of a half wavelength dipole, then compare that radiation resistance, which by the way indicates how well the product radiates, how well the antenna radiates. Compare that radiation resistance with the radiation resistance of a dipole that's 1/20th of a wavelength long. Then maybe what you do is take 20 log of the ratio of the radiation resistances, and that'll give you an idea of the dB difference in the ability to transmit or receive of these two antennas. And I think you'll find there's considerable difference. And you probably then could judge that a wavelength over 20, realistically, we could probably think of that as electrically short structure. Let's review a little bit what we've talked about in this first session. The most important idea has to do with current. Keep track of current. We said every current returns back to its source. Currents don't go to ground. I mean, not normally. Yeah, lightning currents and a few other examples may involve currents that are trying to actually flow to Earth or to ground, but most currents are simply trying to find their way back to the source. And when we have electromagnetic interference troubles, usually what that means is a portion of our current, maybe only 1 or 2%, has found a path back to its source that we didn't want it to take, and it therefore interfered with another circuit or radiated energy out into space. We said current takes the path of least impedance. That's how we know where the current's going to go. It's going to take the path of least impedance. That answer is always true. It doesn't matter what the frequency is. Current always takes the path of least impedance. It's a very good idea. It's something you can hang your hat on, something you can count on. But like ideas that are true in all cases, they tend to be a little more difficult to implement, to use. What does least impedance really mean? We have to boil it down to something simpler. Well, if the frequency is less than a few kilohertz, we can simplify least impedance to mean least resistance. On the other hand, if the frequency is above a few kilohertz, say above 10 kilohertz, that'll give us a little margin, then we're pretty sure the current's going to take the path of least inductance. Now, how do we know what path is least inductance? Well, just think in terms of loop area. Smaller loop areas have less self-inductance than large loop areas. That's a very good way to figure out which path the current's going to prefer. Another idea that we introduced, we didn't use it much yet, we'll use it a lot more in future sessions, is this idea. For wiring, and remember this is true only for wiring, this is not true of chip capacitors and so forth that you might use, or chip inductors, lumped inductors and capacitors. But for distributed inductance and capacitance, the LC product is determined by the material properties, and that's usually a constant. So what this tells us is, again, if you have two conductors, if you bring them close together, we know the capacitance increases. And therefore, the self-inductance is going to decrease. And generally, that's the right thing. We're trying to do, usually, most everything we can to keep the self-inductance under control. Now, you could say, well, maybe I'm overestimating the inductance. Why don't we worry about the wiring capacitance? We do worry about it some, but most people who work with digital signals, they say their digital signals are ringing on the edges instead of being severely rounded on the edges. If the edges were rounded, that would indicate that we have a lot of trouble with excessive wiring capacitance, but that's not the way it is. Most of the time the edges are ringing, and that's a clear symptom that our wiring has too much self-inductance. And so because the wiring is 90% of the time the dominant problem that we have, that's why I concentrate on the wiring inductance as opposed to the wiring capacitance. So this is a very useful formula to help us keep track of when we're going to have trouble with inductance. If we're doing something that we realize reduces capacitance, we got to keep in mind that that is increasing the wiring inductance, and that could be a serious matter for us. We may not want to do that. Let's look again at another example of where the current goes. This is a trace over a plane, a conducting plane. This is a side view. The width of this conductor doesn't quite match the width of the conductor here, but I don't think that matters. What's the current going to do start with the high frequency at 1 megahertz? The current's going to go down this center conductor, and most of the current's going to return right underneath that conductor. There's a little spreading. Actually, and in some instances, the fact that a little bit of this current spreads out is of concern to us at high frequency. But the bulk of the current we know is going to be right under the trace above. That's the low inductance small loop area path. What does the current do at 1 kilohertz? Well, for a lot of people, that can be the problem. Some of that current's going to be here. Some of that current's going to be here. Some of that current's going to be there, over there. There'll even be some of the current on the back side. So the problem is at low frequency, currents take all paths available, and that can really be a disaster. We could have more trouble on this circuit board, in this case, controlling the path of the 1 kilohertz current than we might have controlling the path of the 1 megahertz current. How much inductance do we expect in a typical circuit? Well, here's one good rule of thumb to be aware of. If you've got a 3-inch diameter loop, that will have an inductance of a few hundred nanohenries. A few hundred. I can't tell you exactly how much inductance because we haven't determined the wire size, the radius or diameter of the wire. That will be a factor. And of course that will determine whether it's 100 nanohenries if it's a relatively large size wire, or 500 or 600 nanohenries if it's a small size wire. So depending upon the diameter of the wire, it'll vary some, but a 3-inch diameter loop is a few hundred nanohenries. If you wanted to conclude here with a final quick calculation, say we had number 22 gauge wire that's about 1 meter long, wire size is 0.3 of a millimeter, and the wires are about 2 millimeters center to center apart. Because they're pretty close together, I'm now using the hyperbolic cosine formula instead of the logarithmic formula, but in this case we calculate 722 nanohenries. Just one final example. And that concludes our first session.